This is Hartnell Governor. So Hartnell Governor is a spring-loaded type governor. So there are two types of governors. One is spring controlled and the other one is net weight governor. So Hartnell Governor is a spring controlled governor. So there you can see there's a spring, right? So that's why it is called as spring controlled governor. So in this picture we can see the parts of the Hartnell Governor, right? So here is the frame, right? This is a frame. This entire part. This is a frame, okay? And here is the fly ball. So these two are the fly balls which will fly with the increase of speed or decrease of speed, right? Vertical arm, right? So this is the vertical arm since it's vertical, and here is the horizontal arm, right? This is horizontal arm, and here is the pivot. So imagine what will happen when it moves up. This will come like this. When it moves down, this will come like this, right? So we are going to see it in the animation motion, right? And roller. So these rollers are allowed to move within this region, right? Why is it allowed? Because it needs to move so that it can move, right? Then only it can move. Right? And here is the sleeve. Okay, this is a sleeve, and this is a main spindle shaft. Right? So this complete assembly will rotate on this main shaft, right? And this is the input shaft, right? So input shaft, it is connected to the engine, all right? And here is the bevel gears, right? So bevel gears, so input shaft, which is connected to the bevel gears, will rotate this assembly, right? And this is the collar, right? And here we have a bell crank lever, and this lever is connected to the throttle valve, right? So throttle valve, the airflow, sorry, the working fluid supply, this is in, this is out. So based on the motion of this mechanism, this will either open or close to regulate the flow of this working fluid, right? So there you can see how the functioning of this, right? So this is how it will function. When this complete assembly rotates, either this may contract like this or this may expand like this. So this is all the motion of this Hartnell governor. Right? Up and down movement of the sleeve makes the lever rotate to actuate the valve disc. Right? So you can see the motion of this one up and down will allow this one to control this one. Right? And here is the maximum position, and this is the mean position. Right? You can see, and this is a minimum position. So this is a range, the minimum position and maximum position, that's the range. So this range is controlled by this spring, you can see. So this spring is contracted now. Now it's little bit expanded, and when it's come down, it's completely expanded. That's why it is called as spring controlled governor, right? So this is why it's called as spring controlled governor. And here is our vertical arm, horizontal arm, fly ball, right? Sleeve, and here is our lever, which is connected to the throttle valve, right? So when you see the actual motion, this also going to rotate, right? So when the shaft rotates, the bevel gear rotates. When the bevel gear rotates, the sleeve will rotate. When the sleeve rotates, the complete assembly will rotate, right? So what's happening? Arm expand due to centrifugal force, right? So when the motion, you can see, when the speed is low, arms contracted, right? It's contracted. When the speed increases, you can see the arms are expanded. When you see the arms are expanded, so this is expanded position. Arms contracts and come down due to recoil force of the spring. So when this spring recoils, the arms will contract like this, right? So there you can see now it is, the speed is decreasing, the arms are contracted. You see here, the arms are contracted, right? And the spring is in initial position or recoil position. And here is the shaft which is connected to the input speed from the engine, right? And there you can see the functioning of this one, right? What's happening when the engine speed decreases, right? When the engine speed decreases, what should be done? Engine speed need to be increased, right? So if the engine speed need to be increased, what should happen? The flow should be high, which means the valve should open. So what's happening here? Arm contracts, pushes the sleeve downwards, right? So when the speed decreases, you see here, when the speed decreases, it pushes the sleeve down, which in turn rotates the lever open. You see here, at this position, the lever is almost open, which means much amount of working fluid can be supplied. Right. On the other hand, when the speed is high, right? So when the speed is high, what will happen? The arms will open, right? So when the arms open, here you can see now the speed is high, right? Speed is high and the arms are open, right? Arms are open. So if the speed is high, what should be done? The speed should be decreased, right? So if the speed is to be decreased, what should be done? The amount of supply of the working fluid should be reduced, right? So here you can see, right? When the speed increases, the arms open, which will activate the lever in a way that it's almost closed so that it will allow only a limited amount of working fluid, right? So here you can see when the engine speed increases, the arm expands, pulls up the sleeve, right? The sleeve is pulls upwards, which in turn rotates the lever and close the valve to decrease the output flow, right? So here is output flow and here is input flow. So the valve is almost closed when the speed is high, right? When the speed is low, you can see when the speed is becoming low, it's about to open, right? So when it's open, it can supply more amount of working fluid and then it will increase the speed, right? So this is how the Hartnell Governor functions, right? It's controlled by spring and this is how the functioning of the Hartnell Governor is, right? Hartnell Governor. A Hartnell governor is a spring-loaded governor as shown in this figure. So we have already studied that there were two types of governor. One is based on the weight and the other one is based on the spring force, right? So this one is controlled by the spring force. As you can see here, there's a spring, right? So this one is controlled with the spring force. It consists of two bell crank levers pivoted at the points O to the frame, right? So here is a point O and this is another point O. So these two are the bell crank levers, right? So as you can see, this one and this one are the bell crank levers, right? Two bell crank levers fixed to this point O to the frame. The frame is attached to the governor spindle, right? So this frame is attached to the governor spindle, right? Here's the governor spindle, and therefore rotates with it, right? So since it is attached with the governor spindle, this one will also rotate with the governor while it rotates. Each lever carries a ball at the end of the vertical arm OB, right? So each lever, these bell crank levers, will carry a ball here, right, at the end of this point OB, right, and a roller at the end of the horizontal arm OR, right. At the end of this horizontal arm OR, there would be a roller. Why there's a roller? Because what will happen if you imagine when this one rotates, right? So when this one rotates, this bell crank lever either will move inwards or outwards, right? So what will happen? It may take a position something like this, or position something like this, right? So either this could be the position when the speed is minimum, or this could be the position when the speed is maximum. So when the speed is maximum, we know the centrifugal force is high. So what will happen? This ball tend to move outwards, right? When the speed is low, this may tend to move inwards, right? So this could be the two positions, two possible positions based on this bell crank lever, right? So each lever carries a ball and a vertical arm OB and the roller at OR. So why we have this roller arm? Because this also need to be moved either by this way or this way, right? From this equilibrium position, right? Either it may have to move this way or it may have to move this way, right? So to allow this movement, we have a roller here, right? So roller here. A helical spring in compression provides equal downward forces on the two rollers through a collar on the sleeve, right? So there's a spring which will provide the force on the sleeve through a collar, right? The spring force may be adjusted by screwing a nut up or down on the sleeve. So this adjustment can be made either by screwing a nut, either by tightening the spring or a little bit loosening the spring, right? Like we can have here. Okay. So this is how a Hartnell governor will function, right? So let's consider the terms used here. Okay. First, as usual, small m. Small m is the mass of the balls, right? Small m is the mass of the balls. And capital M, which is the mass of the sleeve or central load, right? So small m is the mass of this ball, and capital M is the mass of the central load or sleeve, right? Then R1, right? So these notations are very usual, right? Very usual, except for these two terms, right? So rest of them we have already used in other types of governors also, right? R1 minimum radius of rotation in meters, right? So when the ball make a angle like this, the minimum rotation makes, that is R1, and maximum radius of rotation in meters, right? So when the speed is maximum, that may take something like this, right? So at that point, the radius will be maximum, and that is R2, right? Similarly, omega 1 angular speed of the governor at minimum radius, okay? And omega 2 angular speed of the governor at maximum radius, right? So R1 minimum radius and omega 1 angular speed at minimum radius. R2 maximum radius, omega 2 angular speed at maximum radius, right? So these are the familiar terms. Now we are introducing two new terms which we have not seen so far with other governors, Broiler governor, Watt governor, and Water governor, right? So this is spring force, right? Why we have a spring here? So the purpose of the spring is to control the movement of the balls and thereby control the movement of the governor, right? So spring force exerted on the sleeve at omega 1 in newtons, right? So spring force, right? Spring force exerted on the sleeve, right? Exerted on the sleeve when the angular speed is omega 1, right? So when the angular speed is omega 1, the spring force is S1. And similarly, when the angular speed is omega 2, the spring force is S2, right? So this is a force exerted on the sleeve, right? So we have sleeve. So this is a force exerted on the sleeve, right? And then you have FC1, right? So FC1, as we have seen already, that is centrifugal force when the omega is omega 1, right? So at minimum speed, force C1, that is centrifugal force at minimum speed is mR1 omega 1 squared, right? So when the radius is R1 and when the angular speed is omega 1, the centrifugal force is mR1 omega 1 squared. Similarly, centrifugal force at maximum, that is mR2 omega 2 squared. R2 is radius at maximum speed, at omega 2 maximum angular speed, right? So centrifugal force Fc2 is equal to mR2 omega 2 squared, right? Then we have stiffness of the spring. So we know if there's a spring, there should be a stiffness to a spring, right? So small s is the stiffness of the spring or the force required to compress the spring by 1 millimeter, right? So we know stiffness means the force required to compress the spring by 1 millimeter, right? So small s is the stiffness of the spring, right? So if s is the stiffness, we know s into the length move. Either we can denote it by h or l. So S into H will give you the spring force, right? Why? Because this is the force required to compress it by 1 millimeter into the length compressed will give us the force, right? And then we have X, length of the vertical or ball arm of the lever, right? So X is the length of the ball arm, right? X is the length of the ball arm, that is from pivot point to the ball. Similarly, Y is the length of the horizontal sleeve arm to the lever, right? And Y is the horizontal length, that is from pivot point to the axis, right? So this is Y, all right? And then we have R, distance of fulcrum O from the governor axis, right? So R is the distance of fulcrum O from the governor axis, or the radius of the rotation when the governor is in the mid position, right? So we know anyhow this R would be in the mid position, right? Because when the rotation is slow, it would be taking a value something like this, right? When the rotation is at high speed, this may take an angle like this, right? And therefore, we consider this r as the distance of fulcrum O, distance, right, from fulcrum O to the governor axis when at the mid position, right? Governor is in the mid position, so we can consider this as that position, right? So this position can be considered as the mid positions, not this or not this, right? So this is R, right? So now we have come across to the all the terms, right? Consider the forces acting on one ball crank lever, right? So usually what we do, if we have a system like this, we will take only half of the system to solve the numerical, right? So consider one bell crank lever. The minimum and maximum position is shown in this figure, right? So this is the minimum position, and here is the maximum position, right? So at minimum position, it may take a position like this. Since the speed is low, the balls would be inside, and if the speed is high, the balls may be outside. Why? Because high is centrifugal force, so they tend to move outside, right? And here is the mid position, right? Here is the mid position, that is R. So why it is mentioned as R? Because this R will also change as R1 at this point at minimum position and R2 at maximum position, right? And therefore this fulcrum O to the axis is taken as R, which is a constant one, right? So this fulcrum O to the axis won't change, that is R, but from the ball to the axis will change, right? From here to here, that may be R2, and from here to here, that is R1, right? So the minimum and maximum positions are shown there. Let H be the compression of the spring when the radius of rotation changes from R1 to R2, right? So when the radius of rotation changes from R1, that is this one, to R2, that is this one, let it be H, right? So from here, if we take this as the mid position, right, the length here, that is H1, okay, that is H1 from equilibrium position, you can consider O to the minimum position, this is H1, and similarly from the mid position to the maximum position, that is H2, right? Why? This is a Beltran lever, so this is how it will move, right? Either it may move right like this, or this may move like this, okay? So this length is going to be H1, and this length we will consider H2, right? And combinedly, this H1 plus H2 is considered as H, right? So H1, this length, plus H2, this length, is considered as H, which means the distance while the ball rotating at R1 to the distance while the ball rotating at R2 is considered as H, right? So that is H1 plus H2 is equal to H. So let H be the compression of the spring when the radius of rotation changes from R1 to R2. Okay. For the minimum position, that is when the radius of rotation changes from R to R1. Okay. R to R1. So now it is going to change from this R, okay, this R to this R1, which means it started to rotate with a kind of low speed, right? So now it is changing from R to R1. So at this point, we will write some geometrical equations, right? When the radius of rotation changes from R to R1 as shown in this figure, the compression of the spring or the lift of the sleeve H1 is given by H1 upon Y, okay? H1 upon Y. So I wrote it here also, right? H1, that is this length, upon Y, okay? So you can consider it as opposite over hypotenuse as sin alpha, right? Okay, H1 upon Y is equal to A1 upon X, right? So A1, that is this length A1, right, from ball to the this fulcrum axis A1, right? This is A1 upon X. This length you see here, this is X, right? So opposite upon hypotenuse. So this is also theta. This is also theta, right? Theta 1 actually, minimum position, right? So this theta is going to change. So I make it as theta 1. So H1 upon Y, right? This H1 upon Y is equal to a1 upon x. So this a1 can be rewritten as r minus r1, right? a1 can be rewritten as r minus r1. Okay, so r minus r1 is equal to a1. Therefore, a1 is equal to r minus r1 upon x will be remain x, right? So that is r1 minus r1 upon x. Okay. Similarly, at maximum position, right? At maximum position, we are going to write the equation again. Similarly, for the maximum position, when the radius of rotation changes from r to r2, okay, when it changes from r to r2, so that is from mid position to maximum position, as shown in this figure, the compression of the spring or lift of the sleeve can be given by, okay. So now we are going to write for this term. That is h2. This is a change h2 upon y, right? h2 upon y. That is theta 2 is equal to you can consider that is sine, okay. Sine theta 2 is equal to opposite h2 upon y, which will be equal to, here also we have sine theta 2. That is opposite a2 upon this length x, right? a2 upon x. So a2 upon x. This a2 can be written as r2 minus r, right? a2 can be written as r2 minus r. So that is r2 minus r upon x, right? Now we are going to add these two equations, okay? By adding this equation and this equation, what we will be having is h1 plus h2 upon y will be equal to a1 plus a2 upon x, which will be equal to r2 minus r1 upon x. Why this plus r and this minus r will be cancelled out. So if I add these two, right, if I add this equation and this equation, I will be having r2 minus r1 upon x, right? So that is r2 minus r1 upon x, okay. We have already seen this h1 plus h2 can be written as h. h1 plus h2 can be written as h, right? So I will replace this h1 plus h2 by h. So which means h upon y is equal to r2 minus r1 upon x, right? r2 minus r1 upon x. Why? Because h is equal to h1 plus h2, right? So h upon y is equal to r2 minus r1 upon x. If I make h as the subject, right? If I make h as the subject, I will have r2 minus r1 into y upon x, right? So h can be found as r2 minus r1 into y upon x, right? Okay. Now for the minimum position, right? Now we have found the h, r, and some geometrical equation or geometrical relation, right? So we have found some geometrical relation. Now we are going to introduce the force part also, right? So now we'll take for the minimum position, right? So now we'll consider for the minimum position. This is the minimum position diagram, okay? So we'll take moments about point O. Why point O? Point O is the pivot point where the fulcrum is, right? So we'll take moments about point O. So we have three forces. We have Fc1, a centrifugal force, which is acting anti-clockwise. We have another force by mass of the ball, which is acting clockwise, right? We also have a force here at the central load or sleeve as mg plus s, right? Mg is the mass of the central load and s is the force exerted by the spring, right? So that total force into this distance, so that is also in the clockwise direction, right? If I take moment about this one, right? Centrifugal force is anti-clockwise direction, and mass of the ball, which is in clockwise direction, and mass of the central load plus force by the spring is also in the clockwise direction, right? So I'll resolve it into the moment of moment equation, right? So we'll start mg plus s1 in by 2, right? Why by 2? Because usually we take only half of the equation to solve, right? Half, not half of the equation, half of the system, right? So if this is a complete system, right, we'll take only half of the system to solve it. So therefore we have mg plus s by 2, right? s1. Why s1? Because this is at minimum position. So in minimum position, usually we term all the terms as subdivision 1, right? So a1, r1, omega 1, x1, y1, theta 1, h1, right? s1, right? So usually for the minimum position, we term all these terms as with the subscript 1, right? a1, r1 like that. So mg plus s1 by 2, this is force into the distance that is, you can see that is y1, right? So from O, this force is acting in a distance y1, right? So mg plus s1 by 2 into y1 equal to, so this is in clockwise direction, but this is in anti-clockwise direction, therefore equal to fc1 into distance for the fc1 to the O is x1, right? So fc1 into x1, okay, minus y minus, because mg is acting in the clockwise direction but fc1 is in the anti-clockwise direction, so fc1 minus mg into this length. So mg we can see is acting on a length a1, right? So the line of action mg is acting in the length of a1, so small mg into a1, okay. So when you simplify it, okay, I'll multiply the entire equation with 2 and divide it by y1, so I will be having mg plus s1 is equal to, right, I will multiply with this 2 and divide it by with y1, so I will be having 2 upon y1 into fc1 into x1 minus mg into a1, okay. So I'll keep this equation as for the equation for the minimum position, okay. So similarly we can find the equation for the maximum position also, right? So what we have to do, we just have to replace these ones with 2, right? Because why, for the maximum position we have taken the subscript as 2, right? So fc2 a2 r2 x2 y2 s2 theta 2 h2, right? So we'll substitute all these ones with 2, so I'll be having mg plus s2 here, right? mg plus s2 by 2, right, into y2. So this force is acting in a distance y2, right? This distance y2 will be equal to fc2. So this is acting in the clockwise direction and this is acting in the anti-clockwise direction, so therefore equal to fc2 into this length is x2, right? From O to the action of fc2, the length is x2, right? So fc2 into x2 plus mg, right? mg is also acting in the opposite direction, therefore minus, no, that is also acting in the anti-clockwise direction. fc is also acting in the anti-clockwise direction, mg is also acting in the anti-clockwise direction, therefore plus, right? Therefore plus mg into the line of action of m2, mg is a2, right? So mg is acting this way, the length between point O to this length is a2, right? So that is fc2 into x2 plus mg in a2, okay. I'll take this 2 and y to the other side of the equal sign, so 2 into fc2 into x2 plus mg a2 upon y2 is equal to mg plus s2, right? So this mg plus s2 is there. I'll multiply this part with 2, that is 2 into, divide this part with y2, 2 upon y2 into fc2 into x2 plus mg into a2, right? So I'll consider this equation as the equation for the maximum position, right? Now we'll subtract this equation from the other equation, right? Subtract this equation from this equation. So when you subtract, what will be having? We'll subtract this from this. So mg minus mg, that is 0. s2 minus s1, so I will have x2 minus s1 equal to 2 upon y2 into fc2 into x2 plus mg upon mg into a2, right? 2 upon y2 fc2 into x2 plus mg into a2 minus 2 upon y1 into fc1 into x1 minus mg into a1, okay. So when I subtract this from this, I will be having this equation, and we already know that s2 minus s1 is equal to x into x. Why? Because s2 is a force, right? As we have already seen, s2 is a spring force exerted on the slip. s1 is also spring force. S is the stiffness of the spring, right? S is the stiffness of the spring, and h is the length moved, right? H is the length moved, and therefore this is a term force having unit n, right? So here we have stiffness, that is force per some distance, right? So force per millimeter, you can say. And here we have a term that is a length, right? That would be in millimeter, right? So force per millimeter into millimeter, that will give you force, right? So S2 minus S1 is equal to H into S, right? And H is equal to R2 minus R1 into Y upon X. So we have already found H is equal to R2 minus R1, right? H is equal to R2 minus R1 into Y upon X, right? So I'm going to replace this H in the last formula we have found, right? So H is equal to R2 minus R1 into Y upon X. I'm going to replace this one with here, right? And make S as the subject. Make S, small s as the subject. Small s is the stiffness. So small s is equal to S2 minus S1 upon H, right? Small s is equal to capital S1, capital S2 minus capital S1 upon H, right? So capital S2 minus capital S1 upon H. So if we replace this H with this value, I will have S2 minus S1, right? S2 minus S1 into 1 upon H. So if H is equal to R2 minus R1 into Y upon X, 1 upon H is equal to X upon Y into R2 minus R1, right? So I'll be having the spring constant as S equal to S2, the force exerted on spring on maximum position, minus S1, that is force exerted on spring on minimum position, upon R2 minus R1, the maximum radius minus minimum radius, into X upon Y, right? So X, the distance of the vertical column to the vertical ball to the axis, right? So this is the X, and Y, that's the horizontal distance between the ball arm and the spindle axis, right? So that would the uh, that would be the final formula if we make S as the subject, right? You can make any one of these as subject, depend on the question, okay? And therefore, neglecting the obliquity effect of the arms, okay? So we'll see what is the obliquity effect. So these are rotating, okay? These are rotating. So while rotating, they may form some angle, right? So while they form an angle, this X and this X may take formula, you see here X2 and here X1, but this would be so small, this change. Why? Because if I take this as a distance X, and if I draw a arc, right? If I draw an arc, something like this, we know the change would be so small, right? So we can neglect this effect. If it is not given specifically in the question, we can neglect usually, right? So neglecting the obliquity effect, that is x1 is equal to x2 is equal to x, right? So which means x1, this length, equal to x2, this length, equal to x, right? We can consider like this, right? So neglecting the obliquity effect of the arms, and therefore y1 is equal to y1, y2 is equal to y. Not only x, right? So it's in the case of y also, we have y here, okay, y1 here, and y2 here, right? So we can neglect these changes also. Why these changes also very minute, right? So the y1, y and y2, these changes also minute with this angle, okay? So while considering these, neglecting these oblique effects, we will be having x1 equal to x2 equal to x, and y1 equal to y2 equal to y, okay? So you can simply use these terms if it is not specifically asked in the question. And the moment due to weight of the balls, that is mg, okay? And also the moments due to the weight of the balls, this mg can also be neglected. Why? Because the mg here and the force by the spring here are too large compared to this one, okay? And therefore we can neglect them as well. Neglect these terms, small mg, that is with the ball, okay? So if you neglect these terms, we have at the minimum position, right? So after you neglecting all these stuff, and if you see for the minimum position, okay, for the minimum position, what you will be having is mg plus s1 by 2, okay, mg plus s1 by 2, right? So this won't change. Why? Because mg and s are their big forces, they won't change, by 2 into y, right? So in the minimum position it was y1, right? It was y1. But since we are considering y1 is equal to y2 is equal to y, we can replace it with y here equal to fc1 into x. So Fc1, that is a centrifugal force, into x. We now told that x1 is equal to x2 is equal to x, and therefore we can consider this as x. And also we can neglect this term. Why? We have now seen that this mg is considerably very small compared to this one, right? So we can neglect this term. So that is m means 0, which means this term will be eliminated, right? So for the minimum position, you can write this equation as mg plus s1 by 2 into y equal fc1 into x, right? Like this. mg plus s1 by 2 into y equal fc1 into x, right? So I will take mg plus x as the subject. So if you make mg plus s1 as the subject, you will be having mg plus s1 is equal to 2 fc1 into x upon y, right? So this, if we consider the minimum position, neglecting all these terms. Similarly, for the maximum position, right? So for the maximum position, here is our maximum position, right? So what we have done, we have neglected these terms y2, not neglected. We have renamed them with y, right? So mg plus s2 by 2 into y equal to fc2 into x plus in this term is 0. Why? We neglect this term, right? And x2 is equal to x, y2 is equal to y, and therefore we can consider this equation as mg plus s2 by 2 into y, right? mg plus s2 by 2 into y equal to fc2, right? Equal to fc2 into x, right? Instead of x2, I write x, fc2 into x, right? And we have already neglected the small m. So if I make mg plus s2 as the subject, I'll be having 2f2, so 2fc2 into x upon y, right? 2fc2 into x upon y, right? So this is the simplified formula after considering all these adjustments. So subtracting equation 6 from 7, subtracting this from this, I'll be having s2 minus s1, because mg and mg would be cancelled out, right? So s2 minus s1 is equal to 2 fc2 minus fc1 into x upon y, right? 2 fc2 minus fc1 into x upon y, right? 2 fc2 minus fc1 into x upon y. We know that s2 minus s1 is equal to h into x. So as we have seen previously, s2 minus s1, that is spring force, is equal to distance moved h into stiffness s, right? So s2 minus s1 can be written as hs, and h is equal to r2 minus r1 into y by x, right? So that we have already found, h is equal to r2 minus r1 into y upon x. All right. So h can be written as r2 minus r1 into y upon x. All right. So if I use these terms in this equation, okay, instead of s2 minus s1, I can write hs. Okay. So s2 minus s1 is equal to hs, right? hs, and I make s as the subject, right? So if I make s as the subject, s is equal to s2 minus s1 upon h, right? s2 minus s1 upon h. So that is here. Instead of this h, I can write r2 minus r1 into y upon x, right? So if s2 minus s1 is equal to 2 into fc2 minus fc1, right? 2 into fc2 minus fc1 into x upon y, x upon y upon this h, right? This h. This h is equal to r2 minus r1 into y upon x. So h is equal to r2 minus r1 into, since it's 1 upon h, that is x upon y, right? So we already have an x upon y here by s2 minus s1, and now we have another h by y with the h. So what we'll be having, x upon y whole thing squared, right? So s can be written as 2 into fc2 centrifugal force at maximum minus fc1 centrifugal force at minimum upon r2 radius at maximum minus r1 radius at minimum into x upon y whole thing squared, right? So x vertical arm length, y horizontal arm length. Okay. And there can be few notes we can take from this. Unless otherwise stated, the obliquity effect of the arms and the moment due to the weight of the bolts is neglected in actual practice, right? So usually, in actuality also, if it is not stated, the obliquity effect by the arm, that is the change of the arm length by rotation, and the weight of the small bolts can be neglected, right? That can be neglected in usual practice. Then, when friction is taken into account, the weight of the sleeve, that is capital Mg, may be replaced by capital Mg plus or minus F, right? So as we have seen in the Porter Governor, if the friction is taken into account, right, the frictional force F can be taken into account depending on the direction of it. If it is acting along the direction of mass, that can be taken as plus, and if it is acting against the direction of movement of mass, that would be taken as minus, right? So Mg plus or minus F. Okay. Then the centrifugal force Fc for any intermediate position, right? So what we have seen so far is the minimum and maximum position, right? So Fc2 is the maximum position and Fc1 is the minimum position. For any other intermediate position, okay? The centrifugal force Fc for any other intermediate position between the minimum and maximum position at a radius of rotation r may be obtained as discussed below. Okay. So now we have seen for the maximum position, we have seen for the minimum position, right? In case if it is asked to find any intermediate position, okay. Since the stiffness of a given spring is constant, right? So anyhow, the stiffness of the given spring is constant, that is S for all position. Therefore, the minimum and intermediate position, okay. So what we have seen here, we wrote this equation of the stiffness of the spring with maximum and minimum position, okay. We can also from this maximum and minimum position, we can write for the minimum and intermediate position as well as maximum and intermediate position also, right? From this we have to guess. Okay, how to do that? 2 S is equal to 2 into Fc minus Fc1. Previously what we have done, Fc2 minus Fc1, right? So if we are writing it for intermediate position and minimum position, right, we will replace this Fc2, that is maximum, with intermediate. If we are writing for maximum and intermediate position, we can replace this minimum with intermediate position. Okay, so Fc, that is intermediate position. Okay, any intermediate position Fc minus Fc1. Okay, so here it was Fc2 minus Fc1. There it was Fc minus Fc1 upon R minus R1. Okay, so here the radius is R2 when the position is at maximum speed. Here at any intermediate piece, that is R. Okay, so Fc minus Fc1 upon R minus R1 into x upon y whole square. That won't change, right? And similarly for the intermediate and maximum position. Okay, so this one is intermediate and minimum position. So if it is intermediate and maximum position, we have to replace this minimum with intermediate. Okay, so Fc2, right? So we are going to replace this equation with intermediate and maximum, right? Intermediate and maximum. So we are going to replace this minimum term with intermediate term. So that is Fc2 minus, instead of Fc1, I put Fcy. This is intermediate, right? This is intermediate. Fc2 is the maximum, right? Upon R2 minus R1. So R2 is the radius on maximum. R is the radius at intermediate. Okay. So Fc2 minus Fc upon R2 minus R into x upon y whole square. Okay. So from these two equations, right? From these three equations. This is for intermediate and minimum. This is for intermediate and maximum, and this is for maximum and minimum. So comparing all these three equations, we have the spring constant as the same, right? So here also it says spring constant. Here also it says, so it won't change, and therefore this one S is equal to 2 Fc2 minus Fc1 upon R2 minus R1 into x by y whole squared, right? So this is equal to this one 2 Fc minus Fc1 upon R minus R1 into x by y whole square equal to 2 Fc2 minus Fc upon R2 minus R into x by y whole square. So if I equalize this and the previous equation, right? So this equation and these two equation, what will be having? So this x by y whole square will be cancelled out in all three. So I'll be having Fc1 minus, so here you see, so this x upon y whole thing squared will be left out. These two will be cancelled out. So what I will be left with Fc2 minus Fc1 upon R2 minus R1 Okay, fc2 minus fc1 upon r2 minus r1 equal to fc minus fc1 upon r1 r minus r1, right? fc minus fc1 upon r minus r1 equal to fc2 minus fc upon r2 minus r, right? fc2 minus fc upon r2 minus r. Why all three are giving same s, right? Same stiffness. Okay, so these three equations are equal. Okay, so based on that, we can make any of these terms as subject. Either you can make fc2 as subject from this equation and this equation, or you can make fc as subject from this equation and this equation, or you can make fc1 as subject from these equations, right? So based on that, you can make any of the term as subject. So here an example of fc is made as subject. So fc is fc1 plus fc2 minus fc1 into r minus r1 upon r minus r2 minus r1. Okay, so you can take any of these terms fc1 or fc2 or fc as the subject, right? So this is how we make the, this is how we make the notes of this equation, right? So this is a general equation, right? Based on this general equation, we determine some special features, right?